we know that in GSSA, we refer the state variables as the Fourier-like coefficients of the circuit variables. So in this section, let's try to derive those state variables Fourier-like series coefficient. So we do the state variable derivation here. So we have the inductor current and the capacitor voltage as the K state variable, and already we have decomposed it into the sum of three items, right? So we first look at the derivative of the inductor current waveform with K equals to 0. So first, dt of the IL with K equals to 0. And for this one, previously we have learned the derivative operate for the calculation of the Fourier coefficients, right? So remember, so this equals to 0 because K equals to 0 plus derivative of IL over dt, the Fourier coefficients with K equals to 0. And for this one, dIL over dt, we have utilized a generalized equation to describe it by introducing the commutation function, right? So we just replace this by a generalized equation, so which is 1 over L times ut times input voltage minus output voltage. And then we can expand this term, right, into two parts. So this will be equals to 1 over L U T V in 0 T. So we place the time-dependent term outside the bracket minus 1 over L VO 0 T. So that is the derivative for inductor current with K equals 0. And next, we care about what if K equals to 1, right? So second equation. So d over dt IL K equals to positive 1. So this will be equals to same as what we have introduced the derivative operator, right? So this time K equals 1, so here no longer 0. Well, this will be minus j omega times IL plus 1 T plus derivative of dIL over dt K equals to plus 1 T. And similarly, the dIL over dt equals to this expression. So we also replace the di over dt by its generalized circuit equation. So this will be equals to minus j omega plus 1 over L U times V in K equals to plus 1 T minus 1 over L VO K equals to plus 1 T. Okay, that is the second equation. So for the k equals to -1 part, we don't care too much about it because we know k equals to -1 is essentially the conjugate of the k equals to +1. So next, the third equation, we care about the capacitor voltage equation. So the third one. Capacitor voltage with k equals to 0. So this one also equals to 0 plus derivative of VO over dt. Then this one can also be represented by the generalized expression by introducing the commutation function. But for capacitor voltage, we no longer have the U term, right? U term. So this is relatively simple. So it equals to 1 over C times the inductor current part minus 1 over C times the output current part, which can be calculated by Ohm's law, right? So RC, output voltage. Okay, and the fourth equation, we care about the capacitor voltage Fourier coefficient with k equals to +1. So this equals to minus j omega VO k equals to +1 t plus the derivative, right? Derivative of VO over dt k equals to +1 t. Again, this can be replaced by this part, right? This part. So equals to minus j omega VO +1 plus 1 over C IL k equals to +1 t minus 1 over RC VO k equals to +1 t. So for the capacitor voltage part, k equals 0 and k equals 1 are sufficient to fully analyze its information, right? So when we look at this group of equations, we can see that for those parts are relatively simple, right, and straightforward. They can be replaced by x1 to x6 terms. But there are two complicated cases. One is this one, and one is this one. Both of them are kind of the product quantities Fourier coefficients. So our next target is try to solve them one by one. So remember, we have introduced the convolution principle, right? Convolution operator. So we can utilize the convolution operator to solve them. So first one, let's look at the first part, U, V in, 0. So the convolution principle tells us that this Fourier series equals to the sum of a series of products, right? U, like -1 to V in. The rule is that their sum should be equal to this quantity, right? If here is -1, here should be +1. And next, U, 0, V in, 0, plus U, +1 times in, -1, plus dot, dot, dot. Okay, so for this quantity, which is the product of U and V in. So first we look at V in. Let's try to separate. So V in is the input DC voltage, right? If we ignore its ripples, we will consider that V in is a pure DC quantity. If V in is a DC quantity, then you will see that those coefficients will be equal to 0, right? Will be equals to 0. The only part which are not equals to 0 will be V in k equals to 0 item, right? So we will only have this one left, right? We only have this one left. So the convolution can be simplified by eliminating those terms and only keeping this one. And for this V in k equals to 0, because V in is a DC quantity, so this value will just equal to V in. So we'll only have U0 left. And for U0, right? Remember, U is a periodical equation with step function like 1, 0, right? It equals to 1 in mode 1. So U0 is like the average over one switching period. So this will be equals to D, right? Times V in. So this one has been solved as dV in. Next, we are curious about this one, right? This one. Also the convolution, but n equals, k equals to plus 1. So let's write this expression. So U times V in k equals to plus 1. This convolution can also be expanded into the sum of many, many terms. But the rule is that their sum of their subscript equals to plus 1, right? So here is U minus 1 times V in plus 2, right? Plus 2. So sum equals to plus 1. Plus U 0 V in plus 1 plus U plus 1 V in 0 plus U plus 2 V in minus 1 plus dot, dot, dot. That is the convolution expression for this product. So similar as what we analyzed before, if you look at those V in terms, there is only one V in term which are not equals to 0, right? So basically, V in k equals 2 is 0. This is 0. This is 0. These are 0. Only this one is non-zero, right? So this means that we will have this convolution simplified to one item left. And remember, the V in coefficient with k equals 0 equals to V in, right? So this will be equals to V in times U plus 1. So the next step will be try to solve the commutation functions for real coefficient with k equals to 1, right? So we use the definition for the Fourier-like coefficients directly. So we know that for the commutation function k equals to 1, it equals to 1 over t times the integral over one switching period, right? We suppose the switching period is from 1 to t. And u tau e2 minus j omega tau d tau. That is the original definition for the Fourier-like series. And this can be further simplified because ut equals to 1 from 0 to dt equals to 0 from dt to ts. So this integral can be further simplified, right? For dt to t, we don't care about it because this one is 0. Eliminate it. So we only have the 0 to dt left. And for this region, u will equals to 1, right? So we only have the e2 minus j omega tau d tau left. This is very standard integral which you learn in your calculus class, right? So this quantity equals to 1 minus 1 over j omega t times e2 minus j omega dt, right? dt minus 1. Okay, so we have the omega dt part, right? And we can simplify the expression by introducing a variable which we call as alpha. So suppose alpha equals to d omega t. And omega is a periodical period, right? Period. So omega t equals to 2 pi. So this quantity equals to 2 pi d. Then we insert this omega into this expression. So the u k equals to plus 1 can be simplified. For here, omega t is 2 pi, right? So here will be minus 1 over j will be equals to j over 2 pi. And this bracket, we can furthermore utilize the Euler's formula to use sinusoidal functions to denote this exponential function. So this will be cosine alpha. So here is alpha, right? E2j alpha equals to cosine alpha minus j times sine alpha minus 1. So this is from the Euler's formula, okay? And alpha equals to 2 pi d, right? We insert the 2 pi d to here. So cosine 2 pi d minus j times sine 2 pi d minus 1. Then we break the bracket and expand the expression. So this will be the j minus j times j will be equals to 1, right? So 1 over 2 pi sine 2 pi d plus j times 1 over 2 pi cosine 2 pi d minus 1. So that's the complete expression for use Fourier-like coefficient with k equals to plus 1. Then we can insert this back to here, right, to find out the expression for this product's conjugate. I will use a different color. So u v in plus 1 equals to v in times this one, right? So equals to v in dc over 2 pi sine 2 pi d plus v in j time over 2 pi cosine 2 pi d minus 1. Okay, so till now we have fully derived those quantities, right? For the top one, it equals to dv in. For the bottom one, this equals to this equation. And remember, we already introduced the x1 to x6 to represent IL VO's Fourier-like coefficients. Then we can insert all those together back to those four equations to get the differential equation represented by x1 to x6. So let's write it to the left-hand side. So the first one, this one will write equals to d x1, right? Because this quantity is x1. And equals to, here, 1 over L. This one, right? This one is minus x2. Then this one is dv in, right? Minus x2. Next, let's look at this one. So here will be IL plus 1 equals to x3 plus jx4. And on the right-hand side, right, this one is minus j omega x3 plus jx4. And this part is 1 over L. Look here, right? We copy here back to the left-hand side. So sine 2 pi d plus j times cosine 2 pi d minus 1. V in divided by 2 pi L. And this one equals to 1 to L. This is defined as x5 plus jx6. Then the third one, left-hand side, output voltage, capacitor voltage with k equals 0. So this will be equals to d2x2 over t dt. And the right-hand side, here is x1, right? 1 over c. And here, 1 over rc, x2. And last one, so left-hand side is x5 plus x6 times j, right? So dx5 plus jx6 over dt. And the right-hand side here is minus j omega x5 plus jx6. Here is x3 plus jx4, right? So 1 over c. x3 plus jx4. And this one, x5 plus x6j, right? 1 over rc. Okay, so next I will erase the right-hand side of the blackboard. Okay, we have erased the white blackboard. So now we can see that we have obtained 4 critical equations. So let's mark them one by one. So here we mark as equation 1, right? Equation 1. And this one, we mark it as equation star 2. This one we mark as equation star 3, equation star 4. So those 4 equations contains 6 variables from x1 to x6. And those set of variables are important, are critical for us to solve the time domain model for the state variables of inductor current and capacitor voltage. So if we look at those 4 equations, we will see that there are 6 variables. Normally, in order to solve the 6th unknown, we need to have a set of 6 equations. So our next step is we try to extend the 4 equations into 6 equations. So let's look at them one by one. First, look at equation star 1. Star 1 is relatively simple, right? Because x is real number, we just list as it is. dx1 over dt equals to 1 over L d v in minus 1 over L x2. And next is equation 3, star 3. It's also relatively simple because x2 is also a real number. Equals to 1 over c x1 minus 1 over rc x2. And next, let's look at the equation star 2, which is interesting because equation 2, if you look at the left-hand side, it is a complex number, including the x3 as the real part and the x4 as the imaginary part. So this means that the complex equation can be decomposed into 2 equations. The real parts are equal on both sides. Meanwhile, the imaginary part on both sides are also equal. So we can decompose equation star 2 into 2 sub-equations. First one is the real part as dx3 over dt equals to omega x4. We only extract the real parts, right? Minus j squared is 1, so here is x4. Plus v in over 2 pi L sine 2 pi d. And that is this one, this part, right? Real part. Last one will be this part, minus 1 over L times x5. And the second sub-equation corresponds to the imaginary part. The imaginary part on left-hand side equals to the right-hand side. So we'll have dx4 over dt equals to minus omega x3 plus v in over 2 pi L times cosine 2 pi d minus 1. And also here, right, minus 1 over L times x6. Similarly, for equation 4, star 4, we can also expand it into 2 sub-equations. First one is the real part. So we'll have dx5 over dt equals to the real parts on the left-hand side, which is omega x6 plus 1 over c x3 plus minus this one, right? Minus x5 over rc. And then we care about the imaginary part, dx6 over dt. Equals to the imaginary part on the right-hand side. Here is omega minus omega times x5. Here is x4 over c. And here is the minus x6 over rc. If you look at those derived equation 1, 2, 3, 4, 5, 6, the left-hand side is the derivative of the x1 to x6, right? Right-hand side are the sum of different terms. So actually, we finally reach our target. We have 6 unknown and 6 equation, which means that we can solve it, right? And also, we can use a matrix format to simplify the representation by combining those 6 equations into one matrix equation. The left-hand side will be derivative term of the state variables from x1, x2, x3, x4, x5 to x6. And this equals to sum of 2 terms, which is very similar to what we have done for SSA, right? Sum of 2 parts. One is the state variable part from x1 to x6. Plus the input vector, right? So which for here correspond to like this quantity, d v in over L, and here is 0. Third one is this quantity, v in over 2 pi L sine 2 pi d. Here, right, v in over 2 pi L cosine 2 pi d minus 1. Here is 0 and 0. Then we fill the state vectors coefficient matrix by just comparing each line of the equation with each line of the matrix coefficient. So, for example, first line will be, we just fill it. We have only one term which is not 0, right? x2 term, which is 0 minus 1 over L. 4 zeros. Second one, we only have 2 terms, non-zero, 1 over C minus 1 over RC. Third one, x4 and x5 are non-zero. Omega minus 1 over L. And fourth one, x3 and x6 are non-zero. Fifth one, x3, 5, 6 are non-zero. Sixth one, 4, 5, 6 are non-zero. Till now, we have fully derived the matrix equation. So this means if we look at this matrix, we can see that it's, although x1 to x6 are time dependent, but their coefficients, matrix, are time invariant. That corresponds to what we have listed, the basic features of GSSA in the first slide. Okay. Till now, we have fully derived the CCM buck converters state variables differential equation group. And also we represent this equivalent group in a matrix format. This means that based on the initial values for the state variables, we can solve the differential equivalent group. And furthermore, we can plot the time domain waveform for the state variables. So we can establish an accurate time domain model for the switch mode power converters based on the first harmonic approximation.